So this is the Mechanics Homework Booklet question 36. We're asked to give an equation showing how the principle of conservation of momentum applies to colliding snooker balls, shown in this diagram. So we've got two balls travelling together, and then afterwards they're travelling off in the same direction. And what they wanted was simply M1 U1 take away M2 U2, because U2 is in the opposite direction, is equal to M1 V1 plus M2 V2. So the total momentum before is the total momentum afterwards. You could make a very good argument that you really should just write down M2 U2 but use a negative value for U2, but that is what they were looking for. State the condition under which the principle of conservation of momentum applies, and that's when there are no external forces. Any external force will give an external impulse and therefore change the overall momentum. We've got a trolley A of that mass 0.25 kilograms and a second trolley B of mass 0.5 kilograms held in contact on a smooth horizontal surface. A compressed spring inside one of the trolleys is released and they move apart, and A moves off at 2.2 meters per second. We're asked to calculate the speed of B. Well, the initial momentum is 0. Afterwards we've got MAVA plus MBVB. So I've got MA 0.25 times VA 2.2, and because they're going off in opposite directions, minus MB 0.5 times VB, and VB is what I'm trying to find. If I add a half VB to both sides, divide by the 0.25, I end up with VB is 1.1 meter per second. We're also to calculate a minimum value for the energy stored in the spring. So I'll first look at this question and think, oh, energy stored in the spring, I've got to be looking at a half Fx. But actually no, because the energy stored in the spring is getting converted to kinetic energy. So what I've got to do is to work out the additional kinetic energy we've got afterwards. Now again, we've got 0 kinetic energy before, so that is just equal to the kinetic energy we've got afterwards. So I work out the kinetic energy for A using its mass and velocity, the kinetic energy for B using that velocity we've just worked out, and I end up at 0.91 joules. So we've gone from momentum and collisions to using Newton's second law with rates of change of momentum. So we've got rotor blades of a helicopter swooping out a cross-sectional area A. There's the area A, and the motion of the blades helps the helicopter hover by giving a downward velocity V to a cylinder of air density rho. Here is the cylinder, cross-sectional area A, length L. Derive an expression we're asked to for the mass of the air flowing downwards per second. So the mass is going to be rho times the volume, and the volume is A, that area, times L. In 1 second, here's the crucial line, in 1 second the length of the cylinder that's thrown down is V. So I've got rho times A times V, the mass is rho AV. We're then asked to derive an expression for the momentum given per second to the air. Well, I've got a mass per second of rho AV, initially stationary. Its final momentum will be equal to the change of momentum, which is the mass times V. So there's the mass I've got each second, rho AV, times the speed V, so it's rho AV squared. And we're asked to hence show the motion of the air results in upward force F on the helicopter given by that. Well, that's the momentum change per second on the air, that value, rho AV squared, and that's downwards. So the force on the air is the change in momentum per second is rho AV squared downwards. Newton's third law tells me that the force on the helicopter must be the same size but upwards, hence that force is rho AV squared. In part D, we're simply using that with some data that we're given. We're told a loaded helicopter has got a mass of 2,500 kilograms. The air is swept out by the rotor blades is 180 meters squared, and that flow of air supports a half of the weight. What speed must be given to the air by the motion of the rotor blades when the helicopter is hovering? So the point is, when it's hovering, half of the weight is being supported by that, or if you prefer, the weight must be twice that. Simply rearranged put in some numbers, I get v squared is 52.4, give or take, and v is 7.2 meters per second. So some good all-round question looking at various aspects of Newton's laws and collisions, mechanics homework booklet, question 36.